What's the most used man-made material on Earth? I'll give you the answer. Concrete. This is the Concrete Logic Podcast. Have you ever stopped to think about the sidewalks, driveways, bridges, or the buildings around you? They're all made from concrete. So why don't we discuss it more? In each episode of Concrete Logic, we'll explore a unique concrete-related topic with the help of industry professionals shaping the trade's future. We'll talk with suppliers, contractors, architects, engineers, specialists, and even proponents of competing materials. We'll get their views on concrete and their visions for its future. So get ready to mix things up with Concrete Logic, where we turn the spotlight on the material that's everywhere but often overlooked. This is the Concrete Logic Podcast. And now, here's your host, Seth Tandett.
Welcome to another episode of the Concrete Logic Podcast. And today I have Dr. Jon Belkowitz back on the show today. Always a good time to talk to Dr. Jon. So today we're going to talk about what petrography is and what can it tell us. So normally, in my experience, petrography is used to when crap hits the fan. So when a concrete doesn't come up to strength, or we're checking maybe concrete was placed that shouldn't have been placed in a certain area. So they want to check out what it is. So Dr. Jon's going to explain what it is, but it's a pretty powerful tool, helps us diagnose failures, improve mix designs, and I think everyone should know what it is if you have concrete on your project, which every job has concrete on their project. So with that, Dr. Jon,
well,
you could define what petrography is and how it's used in concrete.
So funny enough, I talked to my dad about this podcast since we missed it last week. And he said, it's always good to start with not only a definition, but your closing remarks, what you hope people can learn. So I wanted to define the word petrography first using the Latin, then the Federal Highway Association, and then I wanted to give you my closing remarks, all of which should take about 2 minutes to do. And then from there, go on to what your thoughts are. Does that sound fair?
That's great. Thank you.
So petrography comes from two root words or two words, Latin words. One is actually Petra. In the United States and America, we use petro for petroleum-based products. But in Latin, Petra stood for stone or rock, and graphy is the study of. So petrography is the study of stone and rock. Now, if we go back to the Latin, if we go to the Federal Highway Association, back in 2006, they have this wonderful publication that's all about the historical background of analyzing concrete. And they define petrography as a branch of science of petrology, which in addition to description, classification, includes the deciphering of the origins of rocks, study the relationships between various rocks, mineral deposits, study of the effectiveness of various geologic processes, and unveiling the complex history of rocks. It's a very nice, well-authored sentence there. And they go into the different tools and techniques, which we'll be talking about today, which is petrographic analysis is a powerful tool for understanding and solving concrete durability challenges. I think that's the first thing that you brought up, correct?
Correct.
But then it's not just about identifying the problems, but it's also enabling the civil engineer, the ready mix producer to create a better concrete mix design for value-added and long-term performance. So I think you had brought up ASR or calcium oxychloride formation. It's not just about how we're solving problems that have already happened, being, what's the word, reactive, but being proactive. And that's what I hope to get across to your audience today. Definition, what it is, and then where you would use it.
Yeah, how does it actually apply to concrete, and what kind of information can we get? Explain the process first. Let's explain the process of how you use it.
Okay, so we have two situations, right? We've got somebody who wants to be reactive, which you already talked about, and proactive. So we're going to start reactive first. Let me get a pencil here so I can write some notes and just keep track. So let's say this is reactive. You own a hospital or you're a contractor who builds hospitals, right? Contractor for hospitals. And you get a call from one of the attendees on the floor, one of the floor maintenance guys, that you've got some rubber flooring dimpling. And when you come down to your floor, there's these big old bubbles where all the beds turn. Right? What you would do as the contractor is go take some pictures and call a concrete testing lab to come in, because this is a common problem. Say, hey, what the hell is going on? Why is this falling apart? Now, you might also call the flooring provider and say, hey, what the hell is wrong with your tiles? But let's leave it out of it. Let's leave the litigation side out of it. So what you would do is you would call a civil engineering firm and have them come out, and whether or not they have that skill set, what they're going to want to do is investigate what the hell is going on and why is the concrete doing that? Because putting rubber or vinyl or even asbestos tiles, which we don't do anymore, on top of concrete is not a new thing. And normally, if we keep with our concrete within a certain amount of conditions, whether it's relative humidity or, all of the suggestions that Bob Higgins has, there's a boundary condition that if you stay under the moisture content, the salt content, you can have your adhesive and your tile or your coating stay on for a very long time without it delaminating, tenting, bubbling, the adhesive not working. So what they normally do is, either with or without the tile, they core through the concrete and they'll take samples, right? So what a petrographer does is, where they get a big old cylinder, they'll take slices of it from the top, from the middle, from the lower section, all the way through from the top surface of the concrete throughout the body to the bottom to investigate. Now, normally, and again, this is all dependent on who you're working with, if this is a flooring provider, they don't go deeper than that top surface, subsurface.
Right. First
What
inch.
they're looking for is what is on the surface, and they might do some chemical analysis. They might go subsurface to see, okay, is there finishing issues? Did we not have a CSP, a concrete surface profile? Did they not prepare the concrete? And then they can also look for holes, pores, any irregularities that's in the concrete that would be indicative of what would cause the failure. Now, what Bob brought up is what we're seeing in a lot of these floors is that if we do some type of chemical analysis, which, you have in your ASTM-C 856. You see, I use this thing all the freaking time. This is like the third copy I've got. But it goes over the different techniques that you've got to use to identify what the heck is going on with your concrete. And some of those techniques are examining the chemistry. So for, let's say, a flooring issue, Bob brought up salts. If we have somebody do petrographic analysis with, let's say, I don't know if they're using X-ray diffraction, gas chromatography, X-ray fluorescence. There's so many different types of techniques. But what we're doing is looking for a mass species. So you have, when you make concrete, even if your concrete bleeds, you have a certain amount of sodium, calcium, potassium, magnesium, blah, blah, blah. Say, where did I put my concrete? They're evaluating the top surface that was meant for rubber tiles, and there's 8 to 10 times the amount of sodium and potassium at the surface. What would Bob tell you? Would that floor be successful or unsuccessful?
That's a failure. But how do you know that?
Well, they do. That's what I said. They take the sample, take a little bit off the sample, or they could put it in a scanning electron microscope, and they look at it with a specific set of electrons that go at it.
Oh, okay.
And those electrons bounce back. And with that, we have references that say if electron bounces this direction, it's this type of mass species.
So there's a special microscope that you use for this. I can't go buy one at the store and look at my concrete.
Oh, you can if you want to. It's a very special store. But no, there's a bunch of different microscopes, gas chromatography. There's all this different equipment out there that we have at our fingertips to use. Some of us have all of them. I don't have an SCM. I want an SCM. I work with people who have SCMs, so I get to use them all the time, but I don't have a tabletop SCM. I already tried to convince Whitney of that one, and that was back in like the early 2000s. Didn't work.
Yeah.
But,
what's the SCM before you?
Sure. So that's under ASTM-C 1723. It's a scanning electron microscope. Those scanning electron microscopes are pretty effing cool, just the concept of them. When we use a regular optical microscope, when we either have light shining down on our sample or light shining through our sample, what we're looking at is a shiny sample because we're lighting it up. Well, a scanning electron microscope is... Oh, okay, you're still there.
I'm
A
sorry.
scanning electron microscope is something that's similar in that we are projecting an energy source onto our sample, right? But we're using not irradiant light, we're using an electron source. So the light particles or the energy particles are 1,000 times smaller, if not even smaller, than the waves that we're getting from our light bulb, right?
Cool.
Right? So we're in this vacuum chamber. We got a piece of our concrete, and we're looking at not the concrete itself. What happens is the electrons that we project at the sample, they hit the atoms of the mass species of the calcium, silica, all the different shit in there. Then they bounce off the sample, or excuse me, they hit the mass species. Then an electron is projected off the sample. That electron that is bounced off the sample is called a secondary electron. We catch that on a screen and we turn that into a 3D image.
Ooh, that's cool.
Do you want me to show you one real quick?
Yeah, that'd be great.
So here, maybe I can show you a lot of them real quick.
So while you're doing that, this is a specialty thing, so only certain folks can do this.
Hey, listen, if you want to go get a degree in this, if you want to spend your time as a hobbyist and working with different universities, you could do it as much as you wanted. That's how I started doing this, is just I kept asking people. I was like, hey, can I use your scope, or can I try it out? And you ask enough people, you annoy them enough, they eventually say no, or they eventually say yes. So this is, can you see my screen?
Yeah, that's cool.
So this is from the work I did. So I've done a lot of training, and that's one of the biggest things you need to be a petrographer, whether it's, scanning electron microscopy, or, we've got our other microscopes over here. I think one goes up to 150x and the other one goes up to 1800x. This one is going to 1,000, and I think we have a few images that go up to 20,000x or 200,000x. But what we're seeing here is, you talked about it before, ASR. So this is the ASR gel rosette under a high-powered microscope. So you're not looking at inches. Our scale bar over here on the right is microns. So it's 100 microns, and this is just, there's a lot of scientific value as we get deeper or a higher magnification. But just looking at it, it's a very beautiful image. Oops. So let's see if I got any. So that's all 1,000. You still seeing this?
Yes.
So this is 2,000 mag. And now you can see we're going a little bit deeper into the individual microstructure. Instead of seeing the big gel itself, we're going into the lathe-like or wispy-like fibers that make up the ASR gel. Now, the reason why we care about that is because that fiber-like morphology, the way that the different, for lack of a better term, the gels collide, or the way they stack up against each other, or the crystals, creates a morphology that draws in not only more salt, but water. Now, if we can use a certain chemical to change the morphology of that, like let's say nanosilica, we can change the mechanism of how that water is drawn into the ASR gel and how that ASR gel can thrive and survive.
Yeah.
Does that make sense?
Yeah.
So that's a zoomed in. Man, it doesn't let me. They're just so beautiful.
And it just looks like a bunch of different type or textures. Is that just different samples, or is that just looking at it?
So different samples. So all these different looks to them is the ASR gel with different types of nanosilica or without nanosilica. So the more feathery like, or the more fuzzy like this. So this is a 30,000x, excuse me. So this is looking at the different fibrils of the gel, and this is the reference. So this is without nanosilica, right? And this is what I was talking about. These things line up against each other. They create extremely small pores, and with that, you get this capillary pressure, this pore water suction that drives water into the ASR gel, so it can create more of the expansive gel with salt. Oh, isn't that beautiful?
That's crazy.
Yeah, so the more of the nanosilica we bring to the environment, the more of this that we have, where we lose that wispy like. We have, less of these smaller pores. We have a lot more bigger open pores. So we reduce that capacity for capillary suction, that drawing in of water into the ASR gel. But this is getting into a really specific type for a very specific project. Do you mind if we go back to the failure shtick? So I just want to finish that up. So what we can use is for, let's say, a failure of floors is that top surface to see, hey, did the contractor put anything on it weird? Did somebody not do a good prep? Was there a lot of moisture on the floor? Is there hydrolysis going on? I hate to use post-mortem because that often refers to a person's death, but it's after failure. And it could be anything. We're using it on bridges to see how well bridges are doing, a year and a half into their service life. I was just part of a study that's looking at how cement composition has changed in terms of being consolidated for pavements. And what we're seeing is a segregation of the aggregate from the top surface down through the bottom surface. And you have more of a paste here, which is more susceptible to that early failure, whether it's abrasive wear or plastic or drawing shrinkage. So that's another failure scenario that we can look at. And you could use everything from the low magnification microscopes to the high magnification microscopes that we just looked at here a second ago and get similar images. I don't know if you can say that, but it's images that help you tell a story. And that's what you're trying. It's a story problem. We have a problem here. How the hell did it happen? Now, what we're trying to figure out is we're trying to find clues to help us identify what went wrong. Are we always going to find that? That's the problem, that you might not always either have a petrographer who's good enough, the tools that they have might suck, or they're reading the tea leaves the wrong way. That's why you've got to go through a lot of training, because it's almost like being a medical doctor in that it's never a singular thing. When concrete fails, right? There's normally a coupling event, two things go wrong or multiple things go wrong at a time. Like, for instance, if we're talking about flooring, it's rarely that it was just a moisture related issue. That's, again, I hate to keep going back to Bob Higgins, but that had to have been your best podcast to date. Daniel hasn't stopped talking about it, and he sends it to people and he tells it's required listening.
Good.
Yeah. I'd love to see the numbers on that one. But anyway, something that Bob talked about. He's like, rarely is it a singular event. Rarely is just a moisture. And don't tell me that because I have a relative humidity of 85%, I'm going to be okay. Because if you got a lot of salt at that surface, there's going to be a gradient. There's going to be a moisture draw, whether it's from the ambient environment, if you cut your concrete open or it's still open, or if somehow, I know he doesn't believe in it, and somehow you get some type of negative pressure from, a moisture head underneath the concrete. I agree with him that is rare at best, but that still does happen, especially if you got places in Arizona where you've got geysers coming out of your joints. That's one way of using petrography to identify, hey, it's not just the relative humidity, using this analysis technique like, scanning electron microscopy or the different XRDs, fluorescent, get the different chemical identification techniques to see, hey, there was a urethane still at the surface. There was some fatty esters. Something that shouldn't have been on the surface was there, right? It wasn't just the flooring thing. It wasn't just the adhesive, not being designed correctly, or somebody didn't choose the right one. We chose the right one. Just somebody did something wrong to the surface.
Right.
Now, it could also go the opposite way. Hey, there was nothing wrong with the surface. Perfect CSP. There was no relative humidity. There was no salts at the surface. Somebody just didn't use the right adhesive or the right amount of the adhesive, or they didn't use it the right way. Now, that's being reactive, being proactive. Can we go there?
Yep. I was going to ask that.
So, two people are proactive in the industry: the people who produce concrete and need to know what the heck my materials are going to do to the concrete, whether it's alkali silica reactivity or it's pyrotite attack. Some could even argue that the chemical technique that Dr. Weiss came up with when he was at Purdue for calcium oxychloride formation is another technique. And all of that goes to supporting concrete mix design and, hey, can we use this material? So there is a specific ASTM for petrographic techniques for aggregate, and I believe it's ASTM C5. I'd love to tell you, but they packed my book. Book. We're not moving for another 6 months.
So they ask you to do petrographic effort on stuff they're testing in the yard or?
No. So if I'm the aggregate provider,
Yeah.
I need to get, I can't remember how often it is, whether it's a year, 6 months, but they've got to get a petrographic analysis of their aggregate to look at the mineralogy. And basically, it's what you were alluding to before. A certain aggregate or alkali aggregate reactivity is one of the things. And that's what you're looking at. What you do is you take the rock, and you're looking at the quality of that by taking these very thin samples. What are they? 30 microns thick. And you're putting under a certain polarized light. And from there, what you can see is these beautiful diffraction patterns of the rock. Now, there's certain mineralogies like mica. I think you've seen mica before. That has a certain look to it under light. Now, if you look at certain patterns of rock that we're getting out of this lift, and it shows a very distinct pattern for rocks that are susceptible to alkali aggregate reactivity, then either we have to design that in the mix or that rock becomes, riprap or frickin', landscaping material. Yeah,
Okay.
it depends. Now, folks do the same thing with cement, where they do not only a chemical, they should be doing a chemical analysis every month or every so many tons, which is just using an XRD, an X-ray diffraction, where you're looking at chemical composition, saying, hey, I want to know how much of my tricalcium and dicalcium and silicates are in my cement, my A-lights or B-lights. Not only did we use X-ray D, but we also used microscopy to look at that too. The A-lights and the B-lights have a different look to them, where the tricalcium silicate, or I believe that's the A-lights, have a more of a, hexagonal shape, face cubic centered, so they're more angular, and you see much more of it. You normally have like 50 to 70% tricalcium silicate, what makes up your cement. But then you have your dicalcium silicate, or your C2S or your B-light, which is more rounded. It's more embedded in your tricalcium silicate, and we find less of it.
Do they do this at the point of just clinker or after the grind? So could you talk about a kind of a case study of when someone reached out to you for this?
Most of our case studies are on litigation.
Well, I was hoping you would say, I have a proactive client that we just talked about, because that's one of the misconceptions that I had, was this petrography, at least in concrete, is only used as oh crap, we got a problem.
Right.
But what I learned today was, no, there's actually people that ask for this analysis because they're being proactive, because they want to know what material they're working with. So
right.
That's good to hear. Do you have something like that you can share, or
do?
Okay.
Now, I can go 2 different roads.
Okay.
I have something that we can look at that I did on ASR gel specifically.
Okay.
Something that we already looked at, or with nano silica, or something that I think this is better, where we did a whole bunch of different type of analysis techniques as part of our petrographic analysis.
Let's do the better one, the last one.
Okay, so let's do the better one. Let's do the last one. Hey, thanks for catching me on that, you two. I really do appreciate that.
Trying to keep us all out of trouble.
It's not us that were doing it. Is that in a weird light? Does that look pink to you?
No, I can see it.
Okay. So this was something I want to thank the taxpayer, the American taxpayer, and the U.S. Army Corps of Engineers for paying for my research. Okay, so they did a great job of not only forcing me to stick to gray concrete coming down the chute. Like, John, if this is not helping out the industry, if this is research for the sake of research, then we're wasting time and assets. So this had to be something that could be used in the field. So part of my research was looking at not just the microscopic, but connecting the field macroscopic to the microscopic, and then going even a little bit further, and that was into the nanoscopic. So that's what this whole question is. What is the impact of nanosilica size and surface area on phase development, degree of hydration, and pore development? Now, what we're doing here is we're looking at 4 different techniques. Now, this was not something that we did after the fact. This is something that we did before anybody understood what the hell nanosilica was on the ready mix side. They didn't know good or bad, and we wanted to look at it with open eyes and big bellies, the good as well as the bad. Almost wanted to make it like a product brochure, or have a troubleshooting guide, as well as try this for your next job site. Does that make sense before I go on?
Yes.
So we got 4 techniques here. TGA, which is thermal gravimetric analysis, where we're taking our hydrated sample, Portland cement, water, we crush it up after 28 days into a fine powder. We put it into our thermal gravimetric analysis. We heat it. We either catch the stuff that's coming off or we measure the change in weight, and we differentiate that change in weight over time. It tells us a certain what was in the sample at those temperatures. Was there a lot of calcium hydroxide? Was there a little bit of calcium hydroxide, calcium silicate hydrate, water content, so on and so forth? With NMR, nuclear magnetic resonance, that's kind of like putting your concrete into an MRI, where we're subjecting our sample to a magnetic field, and then when bombarding it with radio frequencies, the silicas bounce out of that radio field or that magnetic field, and then they go back to their original field. Now, that relaxation time tells you at what state the silicone is within our hydrated cementitious composite. Now, you combine that with scanning electron microscopy, which helps us look at the topography, some of what we looked at before of our sample at a microscopic scale, with backscattered electron microscopy, which helps us look at pore structure as well as phase development as well as chemical analysis. We can come up with an overall story, which goes back to our question, what the heck is not just our nanosilica size, but the surface area doing to our hydrating cement? And the reason why I say that is, or asked that question in the beginning, we didn't know that there was a difference between using a 5 nanometer particle and a 100 nanometer particle. We kind of closed our eyes, threw it in the back of the truck, and hoped something good was going to happen. But as we make our particles smaller, that specific surface area is going to have a lot more changes to it, reactivity, dissolution rates, so on and so forth, as opposed to the larger particles. And that's what this was all about. So calcium or thermogravimetric analysis, one of the things that it's been used at for a long period of time is looking at not only the calcium hydroxide content, but it's a backwards way of determining if you have reduced the amount of calcium silicate hydrate content in your mix. And what we get out of it from the nanosilica is that from what we found is, chemically speaking, the smaller we go in particle, the more calcium hydroxide we consume. And we assume that from the consumption of our pozzolanic reaction to create more of our calcium silicate hydrate. So from this information, nanosilica 1 over here in blue was our smallest particle, 3 to 5 nanometers. Then we had 9 to 11 nanometers. And then here was 45 to 47, that nanosilica 3. And in the front, our black and orange were our references, our straight cement, and our 20% Class F fly ash. And what we found, and I believe this is at 28 days, is that using nanosilica, we can have a direct impact on reducing calcium hydroxide content, just as we would with our 20% Class F fly ash, but we're doing it with a significantly lower amount of material. Now, besides using the TGA, we wanted to use another method, and that was that nuclear magnetic resonance. And what the NMR is looking at is the calcium silicate hydrate structure itself. And if you've never looked at a calcium silicate hydrate, I don't know, have you ever looked at one under a microscope?
No. I'm a practitioner, man. I just put concrete.
I don't know, so am I, but I read this shit on the weekends. It looks like a ham and cheese sandwich.
Yeah.
Right? So you have the top portion. Let me see if I could do a laser pointer. You have the top. You see this laser pointer? So the top portion over here is your bread. That's the calcium oxide layers. And this is after all the hydration is happening. This is looking at the calcium silicate hydrate, the backbone of concrete strength. Then in between those pieces of bread, you got your ham and cheese. You got these inner layer dominated silicate chains with water and calcium ions. We call those bridging silicone tetrahedron. And on top of the sandwich, we got these pairing silicone tetrahedron. Now, what we want to do is condense the interlayer dominated silicone tetrahedron. Now, one of the easiest ways for us to see that is using this NMR. And what we're doing is we're trying to increase not only the number of silicone states within this ham and cheese or within the sandwich, but we're also trying to increase the density. So we go from Q0, Q1, Q2 to these Q3 states. So when we put in more of our nanosilica, what we're finding is we're changing up the state, and that's what all these numbers represent. The top portion is our controls, where we have none of the Q3 states. And then once we start adding our nanosilica, we start increasing our Q3 states as well as our Q2 states. So we're densifying our calcium silicate hydrate, which is great for us because a denser calcium silicate hydrate means that we're creating something that's less susceptible to alkali silica reactivity because it's imbibing, it's controlling, it's chemically binding those alkalis, that poor water solution that would contribute to that alkali silica reactivity thriving in. So then what we do is we go to another test where we look at the phase development. Now, this is backscatter electron microscopy. And what we're looking at here is a flat polished sample of our nanosilica, our cement paste only, without nanosilica here on the left. Here it's with too much nanosilica, the smallest nanosilica at a very high dosage, and then a much larger nanosilica at the same dosage at the smaller one. And what we see from this is that, first, too much of a small nanosilica is not a good thing, but we use an image or a grade point counting software called ImageJ to do a surface analysis to tell us how much of the calcium hydroxide we have left over, how many pores, how much unreacted cement, and how much of the calcium silicate hydrate we have. And it's just a point counting system based on the grayscale of what we're looking at under the microscope. But then we come back, or first we do, a chemical analysis to evaluate what color it is that we're looking at. So for instance, if you're looking at this one, this is without any nanosilica. You see a lot of light gray and dark gray in here.
Yeah.
Then when you get to too much nanosilica, you see all that black stuff. That's all the pores and whatnot, right? All the holes. And I think that's easy for us to understand. Yeah. The light gray stuff is unreacted cement. We call that anhydrous cement. Now, the reason why it's light gray, it's getting brighter. It has some things in it that will, hold on to electrons. It'll start charging. If there isn't anything in that space, it won't hold on to electrons, it won't charge, and all we'll see is black, hence we have the pores. Now, what we do is we take this sample, we zoom in on it, and then we use the backscatter electron microscope. It has something called an energy dispersive X-ray analysis tool, which allows us to collect some of those electrons and identify what we're actually looking at, either using a line method or an averaging method or a point method. Okay, so this is something a little bit different. We didn't use this in our research, but this is transmission electron microscopy. We're looking at it at almost like a molecular level. So this is the calcium silicate hydrate under a much higher magnification. And we're going down to those individual ham and cheese layers here, which is a lot higher magnification than I've ever done. I really want to use this type of microscope, but Whitney won't buy one from me. Now,
sounds expensive.
It is freaking, and you've got to get vacuums and special rooms for it that have to be a certain humidity. So this was done by a guy named I.G. Richardson. Some of his work is, just on the calcium silicate hydrate. He's got a paper on like CSH1, CSH2. What we're looking at here is this interfacial zone between, on the right side, we have a very porous outer product of our calcium silicate hydrate. It develops very, very quickly, but it doesn't offer a lot of long-term strength because of the porosity of it. On the left-hand side, we have this inner product, or this globular morphology of our calcium silicate hydrate. A lot denser, a lot stronger, and because of that, it's going to add to our durability. We want more of this on the left and less of this on the right. Now, the stuff here on the left, the better stuff with the happy face, it has higher orders of the calcium silicate hydrate, that Q2 and Q3. Stuff on the right The bad stuff, the bad calcium silicate hydride, the outer product, has a lot more of the Q1 and the Q2 states and has almost none of the Q3 states. Does that make sense?
I think we got to a point where it's over my head, but I generally understand what you're saying and why it's being used.
Right on.
So I guess just to sum up this proactive approach, this sounded like you were doing some research on nanosilica and you were looking at different cases of how much, just as layman terms. So don't shoot me, John.
No, you're great, but you're doing freaking great.
So you were looking at, under this microscope, you were different amounts of nanosilica on. Is that correct?
Right. So,
yep.
Yeah, so we were looking at, here we go. So each one of these, where it says CS1, CS, those are 3 different distributions of nanosilica. And we looked at them in different samples at different dosage rates.
Yep. Understand.
And then what we did is, like you said, that proactive, what the heck is this doing to just cement hydration? Not concrete, but just to the cement, chemically speaking.
Yeah.
And you can't just use one experiment, right? You can't just look at one magnification, and you can't just look at one sample. You've got it. There has to be ad nauseum. There has to be a plus or minus. There has to be a standard deviation, because if you do this the wrong way, you can get erroneous results that really have no meaning to them. So again, it comes with, if you're not using enough experiments to look at it from all different sides, like when you go to a job site, you don't just look at it from the street, right? Right. When you're proactive, go onto the job site, you look at the excavation, you grab the soil, you get the soil tested, right? You see where the water table is, you identify what the structure is and when the maximum loads are. From there, you can understand how you build your foundation. Does that all make sense?
No,
we're taking the same principles here and we're using it, but instead of looking at it in a macroscopic, we're looking at it in a microscopic view. Okay.
So I think we covered, there were several things I wanted to cover. One was explain what petrography was. We did that. 2 was when is it used? We covered that. And 3 was what are some misconceptions of it? And we learned that people actually ask for your services on a proactive basis, which I always thought was reactive. So I guess, could you share, like, how much does this cost? Like, if someone's like, oh, let's go back to a practitioner situation. This is, we're in a bind. Yeah. Something happened out at the job site.
Let's say you got concrete tiles. You make concrete roofing tiles for a living.
Yeah, that guy.
You make $2 million a year, and you sell them for multi-million-dollar homes, right? This is a real occurrence. Now, what you would do is you would notice discoloration, and you would notice it because you would get some calls and complaints. Like, what do you mean discoloration? You would get call after call after call. That's what the practitioner, whether it's the contractor that places them or the person who makes them and contracts them as well, they get a phone call from their owners. Hey, I don't know why, but I got white lines, white streaks, and we're cleaning them, and they're not, acid etch them. They keep calling you, getting from multiple. So now what you do is you go out and you collect some of these panels, and you're standing over them. You're like, what the heck do I do? Well, you didn't design them first. You probably called an engineer. So you're going to call back an engineer and say, hey, I've got these concrete tiles, which people do, and I don't know why they're changing colors. I've been doing this for 20 years, and I've never had a problem with this. This has just happened within the last year. So, we'll collect some questions, but then the question is, how much is it worth to them to do the petrography? Right? If this is a multi-million-dollar deal, then they should probably be contacting their insurance company, and their insurance company will go through the same histrionics that we just talked about, but then they'll look in the yellow pages for a petrographer, they'll interview them, and then they'll hire them, and that's how we'll work with our client. If our client doesn't have insurance or they don't want to go through their insurance company, they'll ask us, well, how much is this going to cost? And to turn on any one of these machines, and I know this is going to sound crazy, but you're talking $100 to $500 just to turn on the machine.
Yep. That's not as bad as I thought you were going to say.
That's just to turn on the machine. That's an hour.
Right.
So $100 to $500 an hour. So you're turning it on every hour after that. And that's just the machine. We're not talking about the petrographer. And then the machine, that's only maybe 15 minutes to like maybe 3 hours worth of work. The real nasty work comes in processing the sample. So you can look at anywhere between $1,500 to $6,000 per sample. And then there, it's anywhere between 15 and 20% of the total working cost is your report cost. It's not an inexpensive endeavor, to say the least. But let's say we're going back to this roofing tile. Well, let's say the guy's like, listen, I don't want to go insurance route. I just want to know what happened. So either I can talk to, the folks that design this, or maybe my raw material providers, and see if I can stop doing this, stop this from happening. That's reactive, but that's a proactive direction that I know I can't sue anybody. I can't go to an insurance company. I'm just losing out of pocket. I still have a business to run. How do I, if I know what's going on, I know how to fix it. Let's say for the roof tiles, if they're doing, what's it called? Precast concrete roof tiles that they're doing in a form. It's a 3 cubic yard mixer that spits out an SCC, and we're noticing telltale signs of, overdosing of the high range water reducer, whether it's waxy, bubbly look on the top surface, or it's an excessive amount of bleed channels that are created that are going from the bottom of the form to the top of the form. And then from there, we're seeing the salts migrate to the surface too. Like that can be changed with something as easy as a mix design. Now, okay, so what did that take us, I think is what you were asking. Figuring that out could have cost somewhere around $15,000 to $25,000. Now, there are some petrographers that will promise you, I need to take one look. It'll take me a few minutes, $1,000 under my scope. For something that bad where you're getting that many tiles, which is normally, if they're doing like a 2 foot by 3 foot tile that's 2 inches thick, you're talking more than one batch of materials, especially if it's 1 million tiles. So cement has changed, aggregate may have changed. Definitely the personnel involved. So you're trying to find a common thread within all these different batches, which is a very hard thing to do. And it takes a lot of samples and a lot of comparing and analysis. And sometimes it's just looking at the same image over and over and over again to see what the details were.
Yep.
Or the difference in the details, excuse me.
Yeah.
So that's very expensive.
Yeah.
Yeah, I try to steer clients away from petrography as much as I can. I know that sounds funny because I'm in the petrography business and people ask, why? And it's because sometimes it might be the exact cost of, replacing or repairing, or it might be more expensive. Like you don't want to go to petrography unless you have to. Mm-hmm. And then the reason why, I've been training for the better part of I started in 2007. So what is it? 19, 18 years that I've been trained to be a petrographer. And all the folks that trained me, they were set to retire in 2018. It's 2025. Some of the best ones are gone. Like my favorite petrographers, if they haven't retired, they're about a year to 2 years away. So that was our biggest problem. We couldn't find a good petrographer. The petrographers that we were using, they just couldn't get their work complete on time. They didn't understand what they were looking at. They were jumping to conclusions. I mean, I hate to say it, but unless you're doing an image counting technique and area fraction analysis, some of this stuff is very subjective. It's which one of these is not like the others. And that can change from person to person in technique and how good they are. So petrography is not inexpensive. The practitioner should know that if they're getting into it, if they need it, better be a damn good reason. I wouldn't just do it for the sake of doing petrography. Aggregate providers, they need to do it. That's ASTMC 295, whatever the hell it is. But there are rare occurrences where you really need to do it. Yeah. Now, hey, if you can work with a university, you've got somebody who's training, they're just learning how to do it. You're not going to get great results, but you can get it at a cost. And that's what I used to do when I was at University of Denver, especially for like metallurgical stuff. Like I was just taking pictures. I wasn't analyzing them, but I still got practice time, scope time in.
Yeah. Well, good. I think we got it all covered today.
Awesome.
For sure. So if you wanted to learn more about petrography, you want to reach out to Dr. Jon, I'll put all of his contact information in the show notes. So please make sure you check out the show notes. And
I tell you, wait a second. There's some petrographers that I'm a huge fan of. Do you mind if I call out some names that are just as good? I mean, they're amazing. And if we're ever stacked and racked on lines and we don't have time to do your work, do you mind if I just call out some names?
Yeah.
There's Hugh Ho from WJE. He is top of the food chain.
Yeah.
Like the stories that man could tell, I'm a huge fan of him. Paul Stutzman, legend in the industry. If you've never read any of Paul Stutzman's works, they're all available at NIST for free, which is a government agency. And some of my earliest training was done under Paul Stutzman at NIST in Gaithersburg, Maryland. Then you have like the freaking, he's like, what's that movie with Keanu Reeves and Patrick Swayze? Point Break.
Point Break, yeah.
Yeah, he's like Patrick Swayze's character in Point Break, but for petrographic analysis. David Rothstein.
He jumps out of airplanes?
Yeah. Yeah, he wears a shark tooth. Like,
Nice.
he is one of the best petrographers and one of the coolest cats. I mean, was the motivation for me to start looking at my PhD. Had a beautiful facility up in Boulder, Colorado. It was just 3 people, him, young lady, or a wonderful lady who worked behind the counter, and the guy who did all of his prep work. And he, I believe, sold to Twining and Company. I believe he retired too. But those 3, definitely my top 3 favorite petrographers. And if I'm forgetting anybody like St. Poole or Darwin, I just didn't work with them enough. There's Daniel Armentrout, who I worked with for my different degrees. There's Frank Fisher. I mean, a lot, but they aren't into concrete. Those top 3 guys, if you guys ever need concrete work. One more, Brian Wolf from SGS, TEC SGS, another amazing petrographer. So, I mean, that's 4 petrographers, and I can't really name others that I think there's just not many out there. So also recognize that as a practitioner, it's just there are slim pickings. So there are enough really bad ones out there, but the good ones are really hard to find.
Yeah. Well, I think you were saying it's expensive, but to me, it's all relative. What's at stake?
Right. And that's what you have to keep in mind.
Yep. All right. Dr. Jon, thank you. You spend a lot of time with me today. Appreciate it. And folks, until next time, let's keep it concrete.
Thanks for joining us for another episode of the Concrete Logic Podcast. If you got value from the show, here's how you can provide value back to support the show. Visit concretelogicpodcast.com and click the donate button to send value back. All dollar amounts are truly appreciated. And now, to close out the show, here's Mike Dunton.
Ring, ring, that alarm always sings. Couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives. Dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or 2. Expect more, it's written in our blood. With wood, iron, and mud. From the swamps to the city, from the Lone Star heat to the woods of the Georgia pine. Good old boys and girls who ain't afraid of getting dirty for a clean time. And if you want to see the fire in a grown man's eyes beneath the hot summer sun, find the wild-eyed boys clocking days and nights, working hard to get that job done with wood, iron, and mud. We work hard for $1, give thanks to the Lord above. The color of our collars ain't white or blue. We're all gray collar through and through. Expect more, it's written in our blood. With wood, iron, and mud. prove.